Your goal in this set of slides should be to learn the basic ideas of chemical stoichiometry. Stoichiometry is the study of the quantitative aspects of chemical reactions. For example, if we begin with 10 moles of one reactant, what amount of the other reactant might we need, and what amount of the product might we obtain? This movie shows the reaction of aluminum metal with bromine, the dark brown liquid in the beaker.
When pieces of aluminum foil are placed in a beaker containing bromine, a violent reaction occurs. The elements react to produce aluminum bromide, which consists of 2 aluminum atoms for every 6 bromine atoms. It is visible as a white powder deposited on the beaker.
The first thing we'll do is establish the formulas for the reactants and products. Here the reactants are aluminum, Al, and bromine, Br2. The product is aluminum bromide. Its formula is Al2Br6. Next, we need a balanced equation. To form Al2Br6, our product, how many atoms of aluminum and how many molecules of bromine are required? Our balanced equation shows us that 2 atoms of aluminum and 3 molecules of bromine are required to produce 1 molecule of Al2Br6. Be sure to notice that there are 6 bromine atoms on both sides of the equation. 3 Br2 molecules produce 6 Br atoms, the 6 atoms that appear in the product. Another way to look at this is that 2 moles of aluminum are needed for every 3 moles of Br2, and that these produce 1 mole of Al2Br6 on complete reaction. Now that we have our balanced equation, we can relate the amounts of reactants and products through stoichiometric factors. For example, in this reaction, we know that 3 moles of bromine are required for every 2 moles of aluminum. This will allow us to calculate, for example, the amount of bromine required if we have, say, 10 moles of aluminum. Here is a stoichiometry problem. What amount of Br2 is required to react with 6 moles of aluminum? The answer is to multiply 6 moles of aluminum by the stoichiometric factor. Here the stoichiometric factor is 3 moles of Br2 to 2 moles of aluminum. When you multiply 6 moles of aluminum by the stoichiometric factor, moles of aluminum cancel out and leave us an answer of 9 moles of Br2. Here is another related stoichiometry problem. What amount of aluminum is required to react with 12 moles of bromine? In this case, we have a given amount of bromine, 12 moles, and we'd like to know how much aluminum is required to react with 12 moles of Br2. Therefore, the stoichiometric factor in this case is 2 moles of aluminum for every 3 moles of Br2. When we multiply the stoichiometric factor by 12 moles of Br2, moles of Br2 cancel out and leave us an answer of 8 moles of aluminum. Let's complete our stoichiometry problem. What happens if we have 12 moles of Br2 and plenty of aluminum to react with all of it? What amount of Al2Br6 will be formed under these circumstances? We do this part of the problem exactly as we've done the others. Here the stoichiometric factor is 1 mole of Al2Br6 for every 3 moles of Br2. Therefore, we multiply this stoichiometric factor by the 12 moles of Br2 that we have in our reaction. Moles of Br2 cancel out, and we find that 4 moles of product, Al2Br6, should be formed. Let us consider one more example of chemical stoichiometry, the reaction of solid white phosphorus with chlorine gas.
The flask contains 0.06 moles of chlorine gas. Into it we put 0.01 moles of phosphorus. The elements react, breaking the bonds that link the atoms and forming new ones to create phosphorus trichloride.
What we would like to know in this example is the mass of PCl3 that is formed if we combine 0.060 moles of chlorine gas and 0.010 moles of P4. Remember that the first thing we do before we can carry out this calculation is to write the balanced chemical equation for the reaction. Then and only then can we calculate the mass of PCl3 formed when the reaction occurs completely. What is the balanced chemical equation for the reaction of P4 and Cl2 to produce PCl3? Remember that white phosphorus exists as P4 molecules. Therefore, one molecule of P4 will produce 4 molecules of PCl3. 4 molecules of PCl3 contain 12 atoms of chlorine. Therefore, we require 6 molecules of Cl2. The balanced chemical equation tells us that 1 mole of P4 will require 6 moles of chlorine gas and will produce 4 moles of PCl3. Therefore, our reactants in this case are in the correct stoichiometric ratio. We have 0.060 moles of chlorine gas and 0.010 moles of P4. Now we can find out how many moles of PCl3 are formed in the reaction. Moles of chlorine and moles of P4 are in the correct stoichiometric ratio. That is, there are 6 times as many moles of chlorine gas as there are moles of P4. Therefore, we can choose either one of these to perform our calculation of the amount of PCl3 formed in the reaction. Let's choose moles of chlorine. If we have 0.06 moles of chlorine, we know that 4 moles of PCl3 are produced for each 6 moles of chlorine gas that are used in the reaction. Therefore, 0.04 moles of PCl3 are formed in this process. If we combine 0.06 of a mole of chlorine gas and 0.01 of a mole of P4, we now know that 0.04 of a mole of PCl3 will be produced. What mass of PCl3 is formed? If we know the molar mass of PCl3, 137 grams per mole, multiplying 0.04 of a mole of PCl3 by its molar mass, we see that 5.5 grams of PCl3 will be produced. Chemical stoichiometry calculations are a very important aspect of chemistry. Let's summarize a few important points. First, in all chemical reactions, mass is conserved. That is, the mass of the products is always equal to the mass of the reactants. Second, your first consideration in doing a stoichiometry calculation should always be to balance the chemical equation. Third, there is no direct connection between masses of products and reactants. That is, you cannot calculate the mass of a product directly from the mass of a reactant. Instead, the connection between masses of reactants and products, and so on, is always in units of moles. You must always convert masses of products, masses of reactants, whatever information you have, to moles of products, moles of reactants, in order to find their connection.